So in sections 5 and 6 of chapter 4, we'll learn about Newton's third law of motion and types of forces, as well as how to apply Newton's third law of motion to certain problems. So in the beginning, I just wrote down for you Newton's third law of motion, which is just whenever one object exerts a force on a second object, that second object exerts an opposite directed force of equal magnitude. So if we have a person moving a crate to the right with 5 newtons, that crate is also pushing the person to the left with 5 newtons or -5, showing this opposite but equal magnitude. But we can also have these situations when something isn't necessarily moving. So a person pushing on a wall with a force of 10 newtons to the right, that wall is also pushing the person with a negative force of 10 newtons. Now we have types of forces. So there are 2 major types of forces, which are fundamental forces and non-fundamental forces. So fundamental forces are just means that all other forces can be explained in terms of them. So examples are like gravity, strong nuclear force, and electric weak force. And strong nuclear force and electric weak force can also be non-fundamental. And non-fundamental are just made through interactions between electrically charged particles. And almost all of the forces discussed in this chapter are non-fundamental except gravity. Okay, so starting with some problems. Suppose the mass of a spacecraft is 11,000 kilograms and the mass of the astronaut is 92 kilograms. In addition, assume that the astronaut pushes with a force of 36 newtons on the spacecraft. Find the accelerations of the spacecraft and the astronaut. So at the end, we'll need to have 2 accelerations. So here they give us the mass of the spacecraft and the mass of the astronaut and the force of the astronaut. And they tell us to find the acceleration of both. So here I drew the astronaut pushing on the spacecraft with 36 newtons, and because of this we also know that the spacecraft is pushing the astronaut with a negative 36 newtons. And with the force equals mass times acceleration equation, we can find the acceleration of both the astronaut and the spacecraft. So with the force of the astronaut and the mass of the astronaut, we'll find his acceleration, and with the force of the spacecraft and the mass of the spacecraft, we'll find the spacecraft acceleration as well. Okay, so now we have a billboard ball strikes and rebounds from the cushion of a pool table perpendicularly. The mass of the ball is 0.38 kilograms, and the ball approaches the cushion with a velocity of 2.1 meters per second and rebounds with a velocity of -2 meters per second. The ball remains in contact with the cushion for 3.3 times 10 to -3 seconds. What is the average net force exerted on the ball by the cushion? So, what do they give us? They give us that the ball approaches the cushion and rebounds, and they give us the mass of the ball, its initial velocity, and its final velocity, and its time. So with these things, we can actually find the acceleration of the ball, because acceleration is the change in velocity over time. And they ask us to find the force, and force is mass times acceleration. So if we know how to find the acceleration and we have the mass, we can just find the net force. So, as I said here, we have initial and final and time. So if we do the math, we'll do -2 minus 2.1 over the time will equal our acceleration, and multiply that times the mass, and that will give you the net force, which is just -472.12 newtons. Now we have another problem that states when a parachute opens, the air exerts a large drag force on it, so the force pointing up. This upward force is initially greater and the weight of the skydiver initially greater than the weight of the skydiver and thus slows him down. Suppose the weight of the skydiver is 915 newtons and the drag force has a magnitude of 1027 newtons. The mass of the skydiver is 93.4 kilograms. What is the magnitude and direction of his acceleration? So we just need to find acceleration. So they give us that the drag force is 1027 newtons and his weight is 915 with a mass of 93.4 kilograms. So we just have to really think of the equation force equals mass times acceleration, because we do know his force and we do know his mass, so technically we can find his acceleration. But remember that it's the net force equals mass times acceleration. So that net force just means the addition of the two forces. So it will be 1027 minus 915 because it's pointing down. And that will just give you an acceleration of 1.2 meters per second squared. Okay, now we have two skaters, a man and a woman, are standing on ice. Neglect any friction. The mass of the man is 82 kilograms and the mass of the woman is 48 kilograms. The woman pushes on the man with a force of 45 newtons due east, determining the acceleration of the man and the woman. So we have, they give us the mass of the man and the mass of the woman. And we know that the woman is pushing with a force of 45 newtons due east, so to the right. And because of this, we also know that the man is pushing with negative 45 newtons. And with these forces, we can, and also the masses, we can find each acceleration. So with the force of the man and the mass of the man, we'll find his acceleration, and the force of the woman and the mass of the woman, we'll find her acceleration. So the accelerations are 0.55 meters per second squared and negative 0.94. Now we have some concept questions. So this concept question states, a father and his 7-year-old daughter are facing each other on ice skates. So you can kind of start picturing the picture I drew in the previous slide, where the two forces are acting opposite each other. So with their hands, they push off against one another. Which one of the following statements are true? So we have each experiences an acceleration that has a different magnitude. That might be or is because they both have different masses, therefore different accelerations. Each experiences an acceleration of the same magnitude. Not necessarily. Each experiences a pushing force that has a different magnitude. We know that for sure is not, because the definition of Newton's third law is that they have opposite direction but equal magnitude. So that just shows that D is the correct one. And we'll figure out A and B through drawing. So we have the father and his daughter ice skating. We know that the forces are equal but opposite direction. But we know that the masses are different, so their accelerations technically have to be different as well. So A is correct.